All right, in this problem, we're going to calculate the angle of twist uh, at end A on this uniform solid circular shaft which has some concentrated moments at A, B, and C, and it's fixed at D here. Okay, and the diameter of the shaft, again, it's uniform, it's solid. The diameter is 1 inch. I've got a shear modulus here of 11,000 KSI. I've used a bunch of double arrows here to indicate the direction of the torque or these concentrated torques here, and I've used the right hand rule. So this is just an indication of what I've done here. Is that if you have a double arrow here, point your right thumb in that direction, and your fingers are going to indicate the direction of that torque. Okay, so that's where it's gonna that's just the notation I've used here, just in case you haven't seen that before. And here, what we want to find again is the angle of twist of A with respect to D. All right, and here this is the symbol we're going to use, a phi for the angle of twist, and then here this is to indicate that A with respect to D here. And really the equation that we're going to use is this angle of twist equation. You might have seen it as phi equals, like T of x. This is probably how it was derived to you over J of x times G. And this is when you have maybe a non-circular or a shaft that's non-uniform, it's varying, as well as the torque is varying. And so you have to have this as a function of x from some distance to another, and that'll give you this angle of twist. And you can go through the derivation in any textbook or whatever class you're taking with mechanics here. But I want to talk about how to apply this equation here. And this equation only works when you have segments with a constant torque and constant cross section. And that usually only works when you have segments that have concentrated torques applied to it. So the first thing that we want to do here is calculate some section properties. All right, calculate section properties that we're going to use. And really here we've got the material properties already. And the only one that's of any value here is J, this polar moment of inertia, and that is for a solid circular shaft, pi over 2 times c to the fourth. And this is the outer radius to the fourth, or the furthest radius for the solid circular shaft. So this is pi over 2 times 1/2 inch to the fourth, and here this will be just pi over 32 inch to the fourth. All right, and this is constant through the whole shaft, so this is pretty good. Next, what we want to do is calculate. Let's do this over here where I got some space. We want to calculate the internal torques. Internal torques. And in between each concentrated torque, we know that each that basically it's going to be constant in between. So what I'm going to do is I'm going to make cuts. So I'm going to make a cut here, and if I make this cut here, I want to find the internal torque at AB. So here I have this segment. I've cut it here. I've got this torque here of 600 pound-feet. What I do, even though I know what direction it's going to be, I always draw my internal torque here from the cut, TAB. I draw it internally positive, which would be the double arrow facing away from the cut. And so this TAB here, if I sum the torques and call this positive, sum torques equal to 0, that tells me TAB minus 600 pound-feet equals 0. That tells me TAB equals 600 pound-feet. Or, let's see if I convert this into kip inch to match those units over here to kip inch. That's going to be 0.6 times 12, 7.2 kip inch. Okay, there's that. All right, so that's segment AB. Now I look at segment BC. Segment, so this was AB. This would have been segment AB. Okay, and then segment BC here. So I have here, draw a little bit longer, make that cut through this point right here at BC, and I have some torques. I have a concentrated torque here, 600 pound-feet. Another one here at 36 inches over here, going this way of 400 pound-feet. And then here again, my internal torque, I'm going to TBC here, internal torque, I'm going to sum the torques equal to 0 to the right here. So TBC minus 600 plus 400 equals 0. And that tells me that TBC equals plus 200 pound-feet, which is, let's see, 0.2 times 12, 2.4 kip inch. Kip inch. And the positive just indicates that, again, this torque is facing away, and and it's in that direction. This direction is correct, okay, just like with forces here. And then now, when we go to the last segment, segment BC here, segment CD, I have here, bam, maybe a little bit longer, make that cut through segment CD, which means I'm making a cut here and looking at the left side of the cut, okay, just to make sure that's clear. Looking at the left side of the cut, and I've got some concentrated torques here. I've got the 600. Okay, if you allow me to forego units on this one, 400, and then a 300 over here, 300, and then I have my internal torque TCD here, and again, I sum the torques equal to 0. I say, oops, gotta be clear here, double arrow, positive to the right here, globally positive to the right, so that makes TCD uh, minus 600 plus 400 plus 300 equals 0. And that tells me TCD is minus 100 pound-feet. And that converted into kip inch is, let's see, zero point 0.1 times 12 minus 1.2 kip inch. Okay, which means it should be the, really in actuality, it's actually going the other way. All right, so TCD right here. But now that we found all the internal torques, we can now apply the last part, which is this equation here for the angle of twist, the summation here. So 3, let's see, I'll go over here for 3. Why not? 3, uh, apply angle of twist formula. Okay, and one thing that we anticipate here is that all the units should cancel out, okay, and that we should be left with no units, or essentially radians, in this calculation here. Okay, so here I've got this angle of twist formula here. So this phi is the sum of TL over GJ over all the segments that are of interest to us, okay, where we have, again, a constant torque and a constant cross section. So in this case, it'd be TAB LAB over GJAB plus TBC LBC over GJBC plus TCD LCD over GJCD. It's important to note that I didn't include a negative sign here. There's no negative sign here because we're always assuming that this equation follows, this, it was derived based on positive internal torque. Okay, so you let this negative be corrected when you substitute that into here, okay, later on. So here, now we're going to substitute. We know that these GJs are all the same, so JAB equals JBC equals JCD, so that I can factor that out, 1 over GJ times TAB times LAB, and that is, let's see, 7.2 kip inch, all right, times 36 inches, the length of AAB, plus TBC, which is 2.4 kip inch, times 24 inches. Oh, this line is annoying. Right there, 24 inches, plus a TCD, which is minus 1.2 kip inch, times 36 inches right here. And then this GJ, let me put some numbers to that. That GJ, 1 over 11,000 KSI times, can you even see that? Let me do that again one more time. This is 1 over 11,000 KSI times pi over, what was it? Pi over 32 inches to the fourth. And if you look, these units will be kip inch squared, and these will be kip inch squared. And that tells me, once I run through my calculator, this angle of twist of A with respect to D, this right here, when I run through, ends up with 0.253 radians, because these units will cancel out. I am left with this here. All right. Hopefully that was helpful. This was a nice little exercise. Enjoy, like it, and I'll do more. All right. Take it easy.